Hello, welcome everyone to our webinar on Physics AI for Digital Twins for Aerospace and Defense. Today we are going to talk about digital twins, how they are created, how they are used in the aerospace and defense industry, how Physics AI enables digital twins. A few housekeeping items before we get started. Um, at the bottom of your webinar window, there is a toolbar where you can find a Q&A box. So you can use that Q&A chat to post your questions. So we have time at the end of the webinar to answer any of the questions you have. Next to that is also a resources button that you can use to check out various resources related to the topics we're going to talk about today. With that, so just a brief introduction about us. So I'm Dheeraj Vemula. I'm a technical marketing engineer at Luminary. I've been in the simulation space for about 10 years now, doing various different functions like product development, pre-sales, post-sales, application engineering. Uh, Been doing digital twins, physics AI, reduced order modeling, and all of that throughout my career. And I'm joined here with my colleague Andrew, whom I'll let him introduce himself.
Hi, I'm Andrew. I'm an FD here. Primarily do applied physics AI for things like external aerodynamics. Uh, Previously, I was a researcher at Sandia doing a lot of projects related to things like hypersonics and rarefied gases.
All right. Okay, so here's the agenda for today. We'll start with a bit of an introduction to Luminary for those of you who are joining us for the first time. Then we're going to, Andrew's going to talk about the physics AI model that we are going to use to showcase the digital twin applications. Then we go into the digital twin applications themselves. And finally, we'll have some time for the Q&A. With that, who we are, so we are a Bay Area uh, frontier research lab focusing on physics AI applications. So we are helping industries adopt physics AI models for engineering, design, and operations. We are founded by our founder, our CTO is Juan Alonso, who is the chair of Department of Aeronautics and Astronautics at Stanford. We were founded in 2019, and ever since then, we're working on physics CAE space. What we do at Luminary, we have this end-to-end physics AI platform to create physics AI models and deploy them. Um, we also offer industry domain expertise. Specifically, we've worked a lot with aerospace and defense companies, a lot of them focusing on accelerating product development. We know physics AI is a new technology, so we have a value delivery model where we routinely partner with our customers in deploying FDEs like Andrew on site to identify applications for physics AI and deploy them in a meaningful way. Um, and specifically talking about aerospace and defense market, where the market is today. So this is what we are hearing from our customers in the industry. So there are a lot of new entrants in the aerospace and defense, a lot of new startups, which meant compressed bid timelines. So traditionally, there have been years or multiple years long proposal timelines, which are now being compressed into less than a year, a few months. There's also a lot of pressure to deliver the most performance at the least cost. The systems are getting really complex. There are multiple systems coming together, working together, a lot of interactions. That means a lot of risk and failure if not captured early in the design phase. So these are some of the challenges we hear from our customers in the aerospace and defense market. And our solution, or part of the solution, is physics AI. So what is a physics AI? Like any AI model, physics AI starts from data. So we start with either simulation data, large sets of simulation data or experimental data or operational data. So we take that all together on the platform, feed it to a model architecture designed for physics AI, predicting physics as opposed to traditional LLMs or other types of AI models. We train the physics AI model on the data that the customer or the user trusts. And then after that's completed, then we have a physics AI model that can, like a solver, take in a geometry and predict full field physics prediction really fast. It runs on the GPU, inference, or this task of prediction takes maybe a few seconds or sometimes faster than real time. And we do this for different domains. So you can do this, you can apply the same high level approach for structural mechanics, heat transfer, fluid mechanics, material science, or electromagnetics. So, so how does this physics AI capability change your product development lifecycle? So at a high level, if you look at a product development lifecycle, there are these four stages, starting from concept design, going all the way to operations. And physics AI has applicability across all of these stages. In early design phase, so designers often miss the intuition or the physics-based insights for the design changes that they're making, packaging engineers, design engineers, so on. What physics AI offers there is that physics intuition into the design process. Designers can immediately change the design, understand the impact of that design, operating changes in the operating envelope on the performance of the asset. In this case, maybe a missile or an airplane. So physics I can accelerate that. Then when we move to basic and functional design, now we have multiple systems talking together, or this physics intuition moves beyond designers. You want a controls engineer needs to know how the physics changes throughout their operating envelope. Propulsion engineer needs to know how their configuration is affected by the physics, or the physics is affected by their configuration. So uh, people have been using AeroDB models, which are very good for some of these applications already, but they are, at the end of the day, low fidelity models, and that often need fine-tuning and correction. That comes from full fidelity simulations like CFD simulations. So physics AI offers this value in that aspect, in the sense that you can either replace the AeroDB with a fast and high fidelity accurate physics AI model, or use a physics AI model to quickly generate your AeroDB without having to run the full fidelity simulation. Then we go into the detailed design space where now you're locking in onto your design, but then you have specialists working on different domains, like an aerodynamics engineer working on the aerodynamics, a structural engineer working on the structures, in a siloed way, operating and improving the design there. So we want to, but in reality, there's systems are rarely siloed or separate. They're connected, a multi-physics system. So what was prohibitively expensive to understand the behavior in a multiphysics way was these solvers are at different timescales, different meshing resolutions, so on, and it was quite expensive to couple them together. But what physics AI enables is, which we'll see later today, is how you can use surrogate models to exchange physics information easily without having the expert in the loop. And then finally moving to operations, this is where digital twins are most popular, where a digital twin can offer physics-based insights like predictive maintenance or a real-time simulator based on operational data. This again has been prohibitively expensive, because having that high fidelity physics at a speed that's needed for a digital twin wasn't possible without physics AI. So physics AI unlocks all of these applications. We are going to look at three of those four applications today in the interest of time. Uh, Really high level, how an architecture for digital twin looks like, especially a real-time digital twin. It uses sensor or experimental data. Then the core of the digital twin has a physics AI model that is the physics engine that the digital twin predicts. And then sometimes there's also other components like we look later today, sensor fusion, to ingest the data in a meaningful way so that the physics AI model can correct itself. And then often in real world, as the digital twin is operating for several days, hours, it needs correction. So there is often async process where you trigger an active learning so that your physics AI model is again, depending on what it's seeing in the real world, is improved through either simulations or more data, and so that it stays accurate to what it's operating in. And then the digital twin then gives you these physics-based insights that can be used in several different ways, like predictive maintenance or real-time simulators, so on. So with that overview of what physics AI is and how it is connected to digital twins, how it enables digital twins, we'll now talk about a specific physics AI model that we are going to use to showcase these digital twin applications, which is Shift Missile. So Shift Missile is our part of the uh, Shift is our portfolio of large physics models that we use as reference models for a broad range of engineering applications. So what we are trying to do is showcase how physics AI can be applied to different domains. So here's just an example of all the different domains we've done so far: shift wing, shift SUV, CCA, nozzle. So all these different external aerodynamic applications we're also working on. Other types of domains, like we have shift crash for explicit structural mechanics. Then we have shift battery for internal cooling. So this is our portfolio of large physics models to show how physics AI can be applied to different domains. With that, I'll now hand it over to Andrew to go over Shift Missile, specifically how it was created and what makes it so powerful.
Sure. Thanks, Daraj. So this first part is talking about what shift missile is. So as he explained, you can use this for a variety of applications. This one in particular was meant to serve as somewhat of like a foundational model to encapsulate a lot of different types of missiles. So it could be ground to air, air to air, air to ground. And so we included a lot of features, mostly focused on the nose shape, strikes, and tail fins. So we created this very generalized geometry. It includes, I think, upwards of 20 different parameters. Here we'll just focus on a subset, specifically focused on those strikes or canards and the tail fins. And here on the right, you can see that it includes a very wide range of missiles, and in some of these, you could even omit surfaces. So if whether depending on your application or program, this same single shift mouse missile physics AI model that I'll show you would be applicable to a wide variety of different missile types. So for all of these, we actually leverage our own GPU native CFD solvers. In these cases, it's just RANs. And one of the really nice things about how we do these simulations is we use a localized adaptive mesh refinement. So you can kind of see here that on the top right, the mesh adapts near the missile body with lessening strength into the far field. And what this really allows you to do is to really focus on really capturing those complicated structures near the body. So you can see here on the bottom, this is a Mach 2 plus flow. And with a small angle of attacking, you see that there's multiple shocks coming off the body and wakes interacting with those shocks near the tails. And you can see it from the surface, we really capture those complicated surface distributions. So we use this software to actually generate large amounts of data. So for these, we were able to do a single RAN simulation in about an hour using two H100s or two GPUs. And with the infrastructure we have here, we'll actually created the full 6,000 simulation data set in a little under a week. So this kind of tells you at the speed that we can generate this data to start immediately training these models. With any sort of simulation and any physics AI, we always ensure that what we're simulating is accurate and grounded to experiments because the physics AI model will only be as good as whatever data you give it. So this is just a sample of how we do some of our VMV. In this case, we were simulating the Air Force Finner missile to some of the ballistic range experiments done in the past. And you can see that with our solver, we can get really great agreement. So this gives us some confidence that not only is this physics AI model, a very good reflection of simulated data or synthetic data, it's actually a good reflection of what we could expect in the real world. And I think one thing that's always good is, people need to know how accurate these models are, because depending on the program or the requirements, there's a wide range of essentially accuracy that's required and speed. So, with the Civil 6000, we're able to get essentially a near perfect prediction with what we would estimate from CFD. So these plots on the bottom are actually us doing predictions on cases that the model has not seen yet. So essentially our validation and test set. And we go to the next slide. And one thing I want to point out is this is not just like a normal surrogate model or a normal neural net. These are leveraging, kind of the state of the art transformer-based models. So these models were really based on inspiration from existing LLMs, where essentially you are creating these geometry tokens to make inferences based on how these features, for example, how a fin would essentially lead to some flow structure on the surface. And what happens is once you infer on these tokens, you get to see the whole full field surface distribution. So here you can see an example of the pressures on the surface, and we compare them to what we see in CFD. And you can see that for the quantity that we measured, lift and pitching, you get sub% error. And really, this is one of the worst case scenarios in terms of a prediction. You still are within 3% of the drag as well. So you can see that not only do you get a really rich representation of the physics on a given geometry, it is very close to what is we are expecting if you did a normal CFD analysis, which could take hours. And to give you some reference, each of these physics AI inferences only happen on the order of a few hundred milliseconds. And so here we'll move on to, once you have that physics AI model, what happens next? Like how do you use this? So one of the use cases, we've been seeing is this idea of an aero database. So really this has traditionally been used for, GNC, tuning some autopilots, flight simulators, digital twins. And what you're doing is you just want to know, for example, at some configuration, some flight conditions, what are my coefficients, forces and moments. And really what we are seeing is the methods today, there's this trade-off where you either need to accept a pretty low fidelity for very high performance, or you have high fidelity tools, but they're a little too slow for practical use. So some of the things we see is this idea of superposition. So take, for example, you have four tail fins, you could deflect them individually and then superimpose their forces and moments together. Evidently, this is not a really accurate description of what would happen in a real flight. They get to slightly better fidelity. There are some low fidelity tools, mostly based on some polynomial fits, sometimes a little bit better with nonlinear regression. But at the end of the day, all they are doing is actually just giving you some coefficients. And we already know from our experience that these type of coefficient mappings don't do very well when you get to a really highly nonlinear regime. And you really do need to do the full prediction on the surface and integrate from there to get a good estimate of what those coefficients would be in a real flight. Um, and so if we go to the next slide, one of the ideas that, one of the things you can do is once you have this physics model is essentially you use it as like a data engine. So what you can do is you can actually create these specialized models. For example, a specific portion of your flight envelope. Maybe you will predict the forces and moments only in that small subset. You can get equivalent accuracy. It just takes a lot of data. So for example, in our physics AI model, if you wanted to get to, same level of accuracy with maybe a much smaller, more traditional model like a neural net, we have seen that you may need on upwards of tens of thousands of simulations. And really that is prohibitive in a lot of programs where it's just too much of a burden. So you could do a sparse sampling and create the physics AI model. And once you're happy with the accuracy with the small number of subsets, you can quickly generate a huge number of inferences to augment the original simulated data. And with these large data sets, you can now create very high fidelity and very low latency models. So in this case, we have shown that we have seen that we could take our physics AI model, which does an inference on 100 milliseconds, distill it to a much smaller model with a huge database and reduce that latency to only a few microseconds, to a few hundred microseconds. And so really the challenges we're trying to address here with these digital twins is the idea that flight tests are very expensive, same with ballistic ranges. And so there can only be, so many done in a program. And so really we're trying to leverage, all the data that we can get and see if we can really expand a number of test and operational points that we can investigate within a digital twin. So the idea is you create this digital twin, you can ground it to make some experiments, or you can, like, as Diraj mentioned, you can use it as some live real-time kind of health monitoring system by having some essentially real-time data assimilation from some sensors. And so here you can see that this is what I'm talking about. So this is what we'll show in a bit. And what we've done is, we recognize this problem. There's the physics AI model. It can give you very frequent inferences, or the distill model can give you more high frequency, but there can be an existing bias. Um, but with sensor data, it can be real, but it can be sparse, and over time it can drift. So there needs a way to get an estimate of the true state based on these two imperfect estimates. And we can show that essentially you can hook this all up through essentially a sensor fusion block. Here we use ensemble common filter. And from there, you can actually leverage both the real-time data, which is coming in at a high frequency, and because of the low latency of the physics AI or circuit model, you can have this update in real time. And so what you get at the end is a very, as good as you can get estimate of what the actual flight dynamics would be.
And also really fast, right? Like faster than real time.
Yes. So essentially, the dilation of your prediction is pretty small. So essentially, you can do the simulation and real-time flight simulation as fast as you would actually observe. And so here, we'll take a moment to show you essentially like how this all comes together in a demo. So here we've taken our physics AI model, we've distilled it into a lot of smaller models, each of them focusing on one force and one moment. And to this, we've appended a ensemble common filter with some synthetic flight test data with some bias. And the idea is we've also hooked up a guidance and navigation system. And so this missile can essentially self-direct itself to hit this moving target while correcting its state based on the sensor data that is being fed into. And that's what you see at the top right, is where if you see the red is what is the measured data from the sensors. And the green is what is coming out of the common filter after it's been predicted. So in a sense, we have been grounding the physics AI or surrogate model predictions to what you would measure in a real test flight. Yeah, so I'll pass this now to Diraj to talk about more on the multi-physics side.
So you've seen how we take the physics AI model, start with AeroDB, then also maybe replace the AeroDB with a physics AI model in a real-time simulator. Now, there are other downstream use cases, specifically for multiphysics, once you have that physics AI model. And the reason for doing this is some of the challenges we have, specifically from a multiphysics perspective, and even more specifically for aerostructural, is like we've seen, like, for example, a loads and dynamics engineer in aerospace industry would be using lower fidelity DLM, maybe based methods, or using correction factors to infer the loads, the aerodynamic loads that a structure would see. Um, and that often means they have to go back to the CFD engineer in nonlinear flow regimes, uh, or the conditions like what you've seen for shift missile with separated shocks, several different shocks. So that's one of the challenges. The other thing is like downstream, when the aerodynamics engineer and the structural engineer are working separately to optimize the design, they often miss the interactions like the deflections or the fluid structure interaction between the models. And lastly, but not least, we've also seen customers trying to apply uh, these types of digital twins in operations where they can, with few pressure sensors, how can I get more information about what the damage or what the structure is seeing? So the only solution to that is adding more sensors absent of a digital twin that's physics based. So these are some of the challenges downstream of once we get the RDB and the simulator, where do we go next? So how physics AI solves for these challenges is that with the physics AI model, as you've seen earlier, it bypasses all the complicated steps between when you have geometry to when you solve the high fidelity simulation. In this case, a CFD simulation, with replace that with a surrogate model or physics AI model. So because of that and the speed a physics AI model predicts the physics set, you can now use a physics structures engineer, for example, can quickly run a CFD prediction using the physics AI model and input those loads onto his or her structure and do a structural simulation. So what it essentially is doing is getting the expertise of a CFD simulation or aerodynamic simulation into a usable, fast format that a non-CFD expert, non-CFD engineer can use. We can even go a further step from there where you have maybe a structural circuit model, and now you can maybe, instead of doing a complex, computationally heavy FSI, you can do circuit-circuit interaction based FSI, uh, maybe early in the design process, but then the final validation can be your FSI, not having it, which removes the requirement for compute-heavy FSI early in the process. So those are different things you can do. And what I'm going to show now is the one-way coupling of fluids to structures using the surrogate model. Let me see if I can bring that up. So here's a recording because this is full real-time analysis from CFD to structures. It takes about 3 minutes, but I don't want you to sit through all of those 3 minutes. But what we have is a geometry loaded into the platform. We define a Mach number and an angle of attack, and we initially run a physics AI inference. So in the background now of the physics AI model is running on the geometry with those boundary conditions and trying to predict the physics. I'll forward a little bit here. And then once it completed inference in about 40 seconds, now we map those loads to the structural solver, the structural mesh. Um, the surface pressure distributions from the CFD outputs to or the CFD physics AI to the structural mesh. And in the background, we are now running a full solver, structural solver. The structural solver is not a circuit model, but it is using the circuit outputs of the CFD physics AI. And then because this is a simple use case, it's a inertial relief problem with just the surface elements on the missile. It runs really fast, it takes a couple of seconds, and then you have the deformation. This is the one misses stress on the missile. You can also look at the deformation plot of the missile. Um, yeah, so this is how you can have an entire pipeline, CFD2 structures really fast. You can change your operating conditions, do another prediction, see how your structure is affected. You can do a whole trajectory analysis, like what are the different Mach numbers and an angle of attacks that trajectory would see, and run structural simulation on all of those cases to identify the worst structural performance, so on. So let me switch back to the presentation. So here's we're at the end of our talk today. So some of the conclusions or observations that we've seen along the way is for digital twins for aerospace and defense, what they enable is smarter and earlier operational decisions, because you can use these digital twins to supplement or complement your test cycles, so you don't have to do expensive in the field testing. Maybe you ultimately have to do some testing, but then you shrink the amount of tests you do with these real-time, high-fidelity digital twins, which were previously, you know, which was previously infeasible because of the low fidelity assumptions or the speed requirements that are required. We've also shown you how to compress design cycles with physics AI, which provides faster inference, so you can now not only get predictions fast, but also get these predictions in the hands of non-experts who might be using the outputs of physics AI model for their own engineering workflows. So it both compresses your time to prediction, but also it compresses the time it takes for collaboration between different teams, because now you have a model that can run in instantly and without any of the expertise that's required. Um, we're also actively working on operational physics AI. So we are experimenting with larger data sets. We're improving the quality of data sets, augmenting data sets with test and experimental data. As you've seen, we're trying different strategies to improve performance in in the real world through sensor fusion or experimental grounding. We're also trying exciting new architectures. These are specifically created for physics problems. We are trying to make these more grounded in physics through physics-based constraints. And finally, last but not the least, to do this at scale, you need this end-to-end platform. So at Luminary, we've built this physics AI platform so that you can do everything starting from data generation. As Andrew pointed to earlier, we have a GPU native solver technology that can build data really quickly, then go into training, validation, and then finally deployment. So we are also, in addition to all the research on the physics AI side, we are building this platform that enables you to operational physics AI for your product development or operations. With that, we are at the end of the webinar. Um, Again, I just wanted to remind you that the resources are available. You can click on the button and navigate to our resources. Um, And finally, before we move on to the Q&A, we've just shown a subset of all the use cases, all the ways physics AI can be applied. But then there are more ways physics AI can be applied. This is a snapshot of how our customers are using really fast optimization, inverse problems, generative design, digital twins, as you have seen today, model predictive control, where you have a physics-based model inside the controller loop, uncertainty quantification, especially for, again, real-world, real-time applications. So there are different areas where we have deployed physics AI solutions for our customers. So if you're interested, or if your organization is thinking about any of these types of applications or anything related to physics AI, you can talk to us. You can actually scan the QR code that will lead to our contact us page, where you can reach out to us and you can chat more about your application, how physics AI can help accelerate your workflows. Um, and you obviously can reach out to Andrew or I if you have more questions about what we have talked today or in general about physics AI. Now I think we have some time for Q&A. We can.
You might want to keep it on the QR code.
Oh yeah, I'll go back to the QR code. Let's maybe choose. Okay. So we are. How does you want to take that first question?
So we recognize this is a pretty important problem. I think especially when it comes to something like system model engineering, the idea. Oh, so the question was, how does the model deal or work with different uncertainties? uncertainty propagation once they're all lumped into the black box. Um, so these inferences are not just don't have to be just a finite value. We're working toward actually creating uncertainty bands based on these or confidence intervals for each of our predictions. So these uncertainties can come from, if you're familiar with physics AI models or ML models in general, things that are out of distribution, OOD, sensitivity analysis can be quickly done with these physics AI models as well. Of course, in terms of like how much the bias is from experiments, we can also tune uncertainties, and for example, within the ensemble common filter. All of these things can be built on top of the physics AI model. I think in terms of uncertainty propagation is something we have been thinking about a lot because with system model engineering, you may want to do cross iteration between different physics AI models. In this case, there are mitigations and ways to actually reduce the uncertainty so that the predictions don't just blow up. But this is something we're actively working on. In terms of numeric, so the second question by Harry was numerical solvers are approximations of real world behavior. So what extent have you seen experimental data actually improve the performance of the models versus purely simulated? So uh, I think there's a few questions here. So yes, they are approximations, and we try to get as close to them by making sure that we do our VMV. But of course, there may be some bias. There can be also imperfect sensors, imperfect guidance systems. And in this case, you can ingest them directly into the model. And as we are showing that flight sim, if you're doing a real-time calibration based on real-time assimilation of sensor data, you can drive the error down to, sub-Newton, sub-Newton meter. Of course, this really varies on the flight conditions, but I will just say that we have seen a lot of improvement in terms of our predictions, and the inference time doesn't change because the model itself is the same. It's just the type of data it's seeing. So the predictions get better, but the inference time still remains slow.
Yeah, can I just quickly add to that? So there's also a validation use case that we published on experimental grounding. It's on our website uh, based on the NASA CRM. So the strategy was there to apply a corrector model on top of the inference to take into account for the experimental data, the difference between experimental data and the simulation. So you can check that out. So it's a very well public model too.
The next question is, how does your model assist with material selection and design for additive manufacturing? I think I'll start with this. So essentially, the idea is, let's say you do a multi-physics, multi-objective optimization. And traditionally, what we've seen is you'll use some low fidelity analysis tools and query each one of them. In some cases, they're coupled with each other, but in some cases, they're fully independent. You don't need to make this compromise if you use a physics AI model, because essentially you're doing a full surface prediction. There's two things that happen. One, you get a very rich amount of information. So, for example, my background is in hypersonics, so this is an analogy I will use. If you're doing any sort of TPS or thermal protection system sizing, it allows you to, use that and then also do up to multi-object optimization based on center of mass requirements for stability. And on top of that, you would pass those same aerodynamic, aerothermal predictions for the thermal side, but you can also get the aerodynamic loads and pass it to a structural analysis or a completely different physics AI model based on those structural dynamics. And anyone, who has spent some time in these multi-physics modeling, tried a couple different solvers, it's not a trivial task. But with physics AI, because it's essentially mesh independent, it is a lot easier to couple two physics AI models than it is to couple two analysis tools. So when you're doing a multi-objective optimization, you can do the fully coupled multi-physics, not have to compromise on the fidelity and the inference time, depending on hardware, like I mentioned, it can get down to a few hundred milliseconds.
Yeah. Just to add to that, like how can this approach be applied to like additive manufacturing or material selection? So the model architectures that you've seen, they're in some senses a little bit agnostic to the physics type of physics on which they're building. So you can also use this similar architecture. You have to tweak it a little bit, but can use it for additive any simulations or any processes that you're trying to build a physics AI model for. And these models not just use geometry, but can also use other parameters as inputs, like material properties or like process parameters, like your laser power or your cooling power in a powder bed fusion or something like that. So you can, just as for a CFD model, we use Mach numbers and angle of attacks, you can use these process parameters as inputs to run your physics AI model under different conditions, under different process parameters to see which, let's say, material fits best for, in terms of strength for your model that you're trying to manufacture. So you can apply, I mean, the approach itself is agnostic to what type of physics you're trying to model. So you can apply the same architecture to build models. Um, let's see. I think uh, those are all the questions we have for today. Thanks for joining. We hope you learned something new, learned something useful today. Once again, if you are interested in talking with us about physics AI,